Products, what is my challenge in doing so? I can understand that quite simply in terms of an enthalpy and carbon oxidation state. If I take a molecule like methane, the molecules that I want to make from methane are all thermodynamically uphill. Paraffins, larger olefins, or arenes, they're all thermodynamically uphill. If I do this oxidatively, the danger is that I can fall down this cascade and over-oxidize. But if I do this non-oxidatively, I still have to go uphill, right? And the only way I can do this thermodynamically uphill reaction is I have to run at high temperatures where I can overcome these enthalpic constraints. So the entropy of the reaction drives the catalysis. So I need to run this reaction at high temperatures. There's higher. So this puts certain constraints on the single pass conversion that I can get in the catalyst. And that's going to be one of the topics that I'll try and tackle, how to get high single pass conversion in this catalysis. So with that preface, the catalyst that is known to be effective for this chemistry is a HZSM-5 catalyst. It involves, again, I'll show you, there's first molybdenum species that achieve non-oxidatively, there's no addition of oxygen. It does methane dehydroaromatization. It makes benzene at about 70% selectivity. And a number of different groups have reported their ability to both synthesize this catalyst by various methods, as well as achieve this high selectivity to benzene. It makes hydrogen. It does so at high temperatures. I'm at about 700 degrees C, and I'm equilibrium limited to 10% conversion. And it makes, as I said, very valuable products in benzene primarily and hydrogen. So my goals, as I said, in this catalysis are to understand deconstruct the thermodynamic and kinetic barriers that are relevant for this catalysis. But before I do so, let me tell you a little bit about the catalysis or the catalyst under investigation, and then I'll come back to look at what the thermodynamics and kinetics tell us about this catalysis. So what is the catalyst? In our hands, it's a high aluminum content material. It's a silicon to aluminum 11.5. Well, you'll see why this is relevant in a minute. You take molybdenum oxide as a solid, and you mix them and you heat them. The molybdenum oxide first thermally spreads. As you heat it in an oxidative environment, it volatilizes. The moly suboxides that have a finite vapor pressure. It forms, as I hope to show you, exchange moly dimers. And this results in a dispersed molybdenum species that looks something like this. And this is a pre-catalyst for methane dehydroaromatization. But this is why you need high aluminum content materials, because I hope to show you that the moly is anchored on the zeolite. It exchanges for bronzite acid sites, and it forms these molyoxidimers in the oxidized form of the catalyst. I'm going to reduce this, but this is the pre-catalyst that's relevant. So I need high aluminum content materials, and this aluminum content restricts the amount of moly that I can exchange. So there is a certain amount that I want to do, and after that there are no more pairs available, and you end up making sites that are either irrelevant for catalysis or tend to re-illuminate your materials. You need high aluminum content materials. You need low moly loadings. We end up using moly to aluminum about 0.25. And then I have a moly dispersed molybdenum oxide, and the zeolite helps me disperse the molybdenum, at least initially. I'm going to run the catalysis not in an oxidizing environment. I'm going to run the catalysis in methane. I'm trying to do methane dehydroaromatization. What happens when this oxide sees the methane? It tends to reduce this oxidic precursor that I've made on the surface of the catalyst, and I see oxygen come off in the form of water, CO2, and we think you end up forming these carbidic forms of moly. I'll try and show you some evidence for this. I'm going to be a little vague about the speciation because this is not something we can characterize, but there's a lot of other interesting work going on in the literature relevant to the speciation of the molybdenum. There is a distinct difference, so I've been characterizing this as a pre-catalyst. This has well-defined regular structures, whereas this one has carbidic forms. I should be able to access this spectroscopically. Can I indeed see this transformation between this oxidic moly and this carbidic moly? I can. If I do TM, I can see at least larger and larger agglomerates of carburized moly as I carburize the catalyst. This at least shows that there are some moly carbide entities that are as large as a couple of nanometers. I can't tell you this is all the molybdenum in the catalyst, but there are at least some larger molybdenum carbide moieties that are formed during catalysis. So I do see a transformation between the oxide to this carbide. I see, again, spectroscopic signatures in the Raman. This moly double bond O has a very distinct signature, which you can see in the Raman if it's dispersed as such, and then is carburized, then this signature band of this moly double bond O disappears, again evidencing this transformation of this moly oxide pre-catalyst. And if you do X-ray absorption in the Zanes region, you can see an edge 1s-4p transition, again for this moly double bond O. And again, when I expose the catalyst to methane, this disappears, and I start seeing features characteristic more so of moly carbide. So I've been trying to show you so far that we form a moly oxide pre-catalyst that undergoes transformation during DHA. The technique we use day in, day out is the following. I've shown you this already. We think it's anchored molybdenum on the zeolite helps disperse it. If this is indeed anchored as such, when I expose it to methane, I lose some oxygen. I showed you that, or I mentioned that I lose the oxygen as CO2, CO, and water. I should lose 1 to 2.5 oxygens per moly, and if you put an online mass spec, this is indeed what we see. We see that you lose the oxygen from there, and I've also tried to depict it as such that we have anchored molybdenum. I showed you in the TEM that we make larger moly aggregates. Then if this moly is dispersed again outside the zeolite, then I must be regenerating some acid sites. I should be able to evidence that as well. These acid sites should come back, and we do that by using dimethyl ether titration. If I have acid sites, dimethyl ether stoichiometrically titrates those and makes persistent methyls. And indeed, during this carburization period, if I note, I can stop at intervening periods and count my acid sites. My acid site density actually initially increases as I remove that moly that's anchored on the zeolite. And then at some point, of course, this catalyst does deactivate, and I'll discuss that as well. So at least in our hands, you have to take a high aluminum content material. You have to make moly, you can disperse the moly very effectively by simply doing vapor phase ion exchange. And that moly oxide is a pre-catalyst that subsequently carburizes. So you do deposit some carbon on the moly, and this is a topic of current investigation in our group. But the other characteristic of this catalyst which will become relevant is the following. You see an initial period of time where you lose this oxygen. During this time, there's no benzene being formed. That's why I've been characterizing this as a pre-catalyst. You see no benzene being formed. Only after most of the oxygen is gone, you start seeing hydrocarbons come off. So this catalyst has to undergo a transformation, actually form under reaction conditions, form this carbide, and then it's active for DHA catalysis. And then you get data that look like these. Okay? You get data, initially the conversion is 20%, that's not limited by equilibrium, it's a stoichiometric reaction. I'm using that methane stoichiometrically as a reductant. Only after I have carburized the catalyst do I see this 10% equilibrium conversion limit, which I told you is what thermodynamics reduced me to, because this is the catalytic function. And I get data that look like this. These are benzene. It's about 70% selective to benzene. This is a small period of time, a period of a few hours, during which the catalysis looks relatively stable, and then the catalyst deactivates. This is a persistent problem with this catalysis, and one we're spending a lot of our time trying to understand now. But I will use this characteristic of the catalyst. This will become very relevant in a few minutes. This deactivation behavior allows us to understand the reaction network that is very hard to do except in this circumstance. So now I want to go back to the questions that I wanted to ask. This is the catalyst that I'm working with. It's a high aluminum content material. It has dispersed moly that appears to have carburized. Now I want to go back to understanding what are the thermodynamic and kinetic influences in this catalysis. Can I deconvolute them? So I hope to show you, if I want to examine the kinetics of methane to benzene, now the thermodynamics, I at least need to understand the network of the reaction. And I hope to show you that the reaction network is sequential. It is a sequential dehydroaromatization reaction where the only primary product you make is ethane that subsequently goes on to form acetylene in very small quantities. If you don't look for this acetylene, you won't see it. And it's this acetylene that is a key kinetic intermediate in DHA catalysis. It will be involved in several kinetically relevant steps. I hope to show you then, based on this reaction network, that I can deconstruct the thermodynamic and kinetic influences and come up with a forward rate of the catalysis. That is the intrinsic catalytic behavior, that is the upper bound on this catalyst. That's as good as this catalyst can be. And then, last but not the least, after I found out how good this catalyst can be, I cannot make it better. The only way I can make it better is I am left with those thermodynamic constraints that I still have to overcome. I hope to show you that by adding an adsorbent that will absorb my hydrogen, I'll be able to remove single pass equilibrium conversion. It's a polyfunctional catalyst with a catalyst absorbent function that will allow me to remove hydrogen at high temperatures. Unlike a membrane, it will allow me to remove the hydrogen where I want to remove the hydrogen and allow me to enhance single pass conversion. So that's my goal in doing so. Again, first and foremost, I need to understand what the network of the reaction is, and I'm going to go back to these data. If I look at the conversion versus selectivity characteristics of these data, as the catalyst deactivates, I get a trend like this. This is a selective catalyst to benzene, as I mentioned. I let the catalyst deactivate, and I see a characteristic that looks as follows. I do an independent experiment. So I do an independent experiment where I again take a different loading of catalyst. I see data that look like these. So my catalyst deactivates. These profiles are congruent. I do another experiment. I see data that look like these. What does that mean for these profiles to be congruent? It means that the catalyst deactivates non-selectively. And what I mean by non-selective deactivation is the number of sites changes, but the characteristics of the sites don't change. It's the same catalytic site, it's just I keep reducing the number. So my bed effectively keeps becoming shorter and shorter as my catalyst deactivates. And this non-selective deactivation allows me to essentially get a profile in time, which essentially gives me an axial profile in the reactor. Okay, so the temporal evolution of the products is actually giving me what's happening actually in a sequential reactor as I go along the length of the bed. And this is the virtue of this, of understanding what the deactivation characteristics of this material are. I see data that look like these. If I take this C2 profile and go in a little more detail, what I see is I see ethylene, I see ethane, and I see acetylene at very low conversions. If you don't examine this catalyst at low conversions, there's a tendency in this catalysis to run high conversions, close to equilibrium. You do not see these molecular characteristics of acetylene. And if you really want to understand what the primary products are, you have to let your catalyst deactivate a lot. If you go to 0.05, 0.01% conversion, these are again multiple sets of data, you can see what the primary product is. The primary product of this reaction is ethane. You see sequential reactions of ethane, you see ethylene, you see acetylene. You see this acetylene at low conversions, and the hydrogen partial pressure is low. The hydrogen pressure is high, you will see very little acetylene in your output. And I'll show you this acetylene becomes relevant kinetically in a minute. Okay? So with this network, now I can start understanding, again, what are my thermodynamic constraints on reaction. So to understand the thermodynamics, I'm going to use the approach to equilibrium. How close am I to equilibrium? It's a sequential reaction, and in this cascade, I will see that my approach to equilibrium for the various steps will change. My partial pressure of species is changing along the length of the bed, so will the approach to equilibrium for the various steps. I can write the approach to equilibrium as the ratio of the reverse rate to the forward rate. And the forward rate is what I'm truly after. This is what the catalyst can do, as good as it can do at these conditions. Okay? This is the upper bound on catalytic performance. So this is what I'm truly after. This is the catalyst performance. So, in context of the data that I've shown you so far, in a sequential reaction, every step should have a reversibility less than 1. That is indeed what I see. This is an outlet composition. I'm measuring the outlet composition of these species, and I can plot their reversibility as a function of methane conversion. And I get data that look like, or I get reversibility values that look like this. They're less than 1 for each of these reactions. And if I examine this in a little more detail, I see that methane to ethane, ethane to ethylene are equilibrated at about 3–3.5% conversion. These steps are in equilibrium, and the approach to equilibrium is changing as my partial pressures are changing along the length of the bed, and these steps will not play any kinetic role beyond 3–3.5% conversion. They are at equilibrium. The only steps that are away from equilibrium as my reaction proceeds are the steps that either involve formation of acetylene or consumption of acetylene. Okay? So the reaction network allows me again to examine which steps are away from equilibrium, which steps are going to determine my kinetics, and the reaction network looks like this. And now I can ask which steps are kinetically relevant. To do so, I need to understand, or the method I will use is the degree of rate control, developed by Johnny Campbell and work done by Jim Domestic. But the degree of rate control senses not just these overall reactions, so I can write this reaction network as such. These are overall reactions. The degree of rate control senses in a reaction network like this the reversibilities of the elementary steps in these reactions and their stoichiometric number. Okay? It doesn't sense the overall reactions. Let me just give you an example. So what I mean by that is that I can define the stoichiometric number of the rate determining elementary steps in each of these overall reactions. Just as an example, consider the first step. The first step could comprise of two elementary reactions. It could either be the activation of methane to form methyls at H, in which case it has a stoichiometric number of 6, or it could be the coupling of methyls to form ethane, in which case it has a stoichiometric number of 3. And on this basis, I have to do that for each of the overall reactions. I can define a degree of rate control. This is simply the definition of the degree of rate control. In a sequential network with the reversible reactions, the degree of rate control is a little more complicated than I'm leading you to believe, but I can calculate the degree of rate control of every single step in this reaction sequence and plot that as such. And I see the degree of rate control as a function of methane conversion. There is no single rate limiting step in a sequential reaction network, and the simplest way that I rationalize this is delta G is a function of temperature and pressure, and this partial pressure of all these species is changing along the length of the bed. So my driving force for these reactions is changing as a function of pressure. There isn't supposed to be a single rate limiting step along the cascade. Early on, methane activation is limited. It's away from equilibrium. As I reach 3.5% conversion that I showed you earlier, these steps fast approach equilibrium, methane activation steps. And the steps involving acetylene are the ones that have higher degrees of rate control as I go along my reaction cascade. And those are the steps that are away from equilibrium and determine my kinetics close to equilibrium. If I consider all the steps that involve acetylene, it looks something like this. Acetylene is formed in low quantities, in small, it's not evident high hydrogen pressures. It plays a significant kinetic role, and you can only examine that within this framework of deconstructing kinetics and thermodynamics that I've shown. Okay. So, at least so far, I hope I've shown you that this reaction cascade is sequential. You can examine it in great detail. If you allow the catalyst to deactivate, it allows you to deconstruct the axial profile along the length of the reactor by examining the temporal profile. And acetylene plays a key role in determining which steps are kinetically relevant as you approach equilibrium. But I haven't answered the question that I wanted to answer, which was, what is the upper bound on this catalyst performance? What is the rate? I've shown you which steps are kinetically relevant. I haven't shown you what is the rate. So let me do that. To understand what the rate is, again, I need to look at elementary steps. That's what the catalysis senses. For any step, I can write the rate of reaction as a forward rate minus a reverse rate. I can write that as a ratio as such. And I can write that again as a forward rate times the reversibility of that elementary step. And for an overall reaction, I can combine this formalism to write the rate as the rate of the overall rate times, this is the product of the reversibility of elementary steps in this reaction sequence, these elementary steps that I've been defining all along the way. So can I go and measure this directly in a reactor? The net rate is something that I measure. Reversibilities I've shown you how to calculate, and now I can calculate a forward rate in my catalytic system. So let me try and do that. Think about what you measure when you do an experiment in a packed bed reactor. In a packed bed reactor, when you do an experiment, you get a spatially average rate. Rates are path functions. What happens as you change, this is a balance for a packed bed reactor, and what you measure is a length average rate in a packed bed reactor. But packed bed reactors convey kinetic and thermodynamic information at different scales. Okay? Thermodynamics is path independent, all for reversibility, the only thing that matters is the final pressure. So I get an instantaneous value of the reversibility. The reversibility I measure is simply a reversibility that I measure here. So this function is length average. This function is an instantaneous value. I cannot directly use this value to calculate a forward rate. I need a length average version of the reversibility as well. Okay. So the way to do that, I need to length average this, but I get an instantaneous value. I need to measure this now at different points along the bed. You do this by measuring several independent experiments. So we load different loadings of catalyst, and I get an instantaneous value of eta at the outlet, and I can calculate now my length average reversibility along the length of the bed and calculate my net rate. My net rate goes down as my bed goes longer and longer. I get closer and closer to equilibrium. Okay. My forward rate doesn't change. Now I have a net rate, I have a length average reversibility. I can calculate a forward rate. This is as good as this catalyst can be. And that forward rate is constant. This is what a good catalyst is supposed to do. It's supposed to make and break the same bond at exactly the same rate every time you make it. This is the upper bound on catalyst performance. Now I'm left with a thermodynamic constraint. What this formalism has allowed me to do is to deconstruct the kinetics and thermodynamics in the form of a forward rate and a reversibility. This absorbent is meant to remove the hydrogen from the catalyst at high temperatures. I told you the catalysis is done is close to 700 degrees Celsius. So I need this material to absorb hydrogen at 700 degrees Celsius and thereby circumvent my single pass conversion limit. So the material of choice for us, this is guided by something we saw in the patent literature, is to use zirconium. So how should I test whether this is actually going to work? I'm going to test this by simply taking a bed of zirconium, exposing it to hydrogen-argon mixtures, and I see uptake functions that depend strongly on the function of pressure. So as I increase my hydrogen pressure, I get these heaviside functions. The catalyst saturates in hydrogen, and then it breaks through. Argon, of course, goes straight through. I absorb hydrogen at 700 degrees Celsius. Is this absorbent regenerable? Well, I can simply expose this catalyst to an inert at high temperatures, and I see that my hydrogen comes back off the surface of the zirconium, and I can desorb this hydrogen. This absorbent is regenerable. And I can count how much hydrogen I took up here before I saw breakthrough. I can count how much hydrogen I got off the surface of the catalyst, and I can put those numbers up here. This hydrogen to zirconium is about 1.7. Hydrogen to bulk zirconium, it forms a bulk metal hydride at 700 degrees Celsius. The entire bulk transforms. It transforms to the point that I can go and put this in a diffractometer, and I can see diffraction peaks for zirconium hydride. This material uptakes hydrogen at high temperatures and makes a metal hydride. So I think this has virtue in doing so. And let's see what happens when I add this to my catalyst. But I have to add it to my catalyst. I cannot add it to my pre-catalyst. I showed you this earlier. There's an initial induction period which you carburize. If you add your zirconium here, it cokes up, it removes hydrogen too efficiently. This is not the time to add hydrogen. You need to carburize your catalyst. If you stop, you can expose it to helium and the catalyst comes straight back. But this is the point where you have to add your zirconium. So now I'm going to add my zirconium to my pre-carburized bed and see what the virtue of adding zirconium is. Okay? I'm going to show you these data as product yield and this maximum single pass conversion. This is the baseline case that I've been working with of HZSM-5 that I showed you, about 8-9% conversion. Now I'm going to add zirconium in interpellet mixtures. So what happens when I add zirconium in interpellet mixtures? I get a much higher single pass conversion. I get conversions as high as 27%. And if I want to regenerate this catalyst, I simply do this in an inert gas. My absorbent gets regenerated. And as a control experiment, we did the following. We thought of doing the following. As a control experiment, we thought of preloading the zirconium. If it's a packed bed reactor, we were not expecting any effect of zirconium. We actually did the experiment, and these are the data. It alleviates thermodynamic constraints even when you preload the catalyst. This was very surprising to us, but I'll show you why. You can load this upstream of the bed. You can load this downstream of the bed, and you can load this in stage stratified configurations. In each case, you get benefit of zirconium. Okay? You get higher single pass conversions, you make products with about the same selectivity in terms of aromatics. And the question was, how do these stage stratified configurations work? Zirconium works in every case. Why does it work when I load it upstream? It would not work if it was an ideal plug flow reactor. The only way it can work is if I have axial dispersion in this bed. This bed is able to communicate information forward and backward because hydrogen has such a high dispersion coefficient, has such a high diffusion coefficient that it moves against the direction of convection if we put it upstream. Okay? So the only scenario in which we could work, which we could describe this quantitatively, was developing a pseudo-homogeneous one-dimensional packed bed reactor model. This is what you're used to in writing in your reactor design class. I have a kinetics term, I have a convection term, and I have an axial dispersion term. Okay? I've shown you how to measure the kinetics. I spent some time doing that in the first half of my talk. We know what the kinetics look like. I can deconstruct it in terms of a forward rate and a thermodynamic effect, which is in terms of reversibility. I can non-dimensionalize this equation. I can take this equation, non-dimensionalize it, and I get terms that look like this. This is going to seem familiar in a minute. I get a non-dimensional parameter, which is a Peclet number. This is the rate of convection to the rate of dispersion. The convection I know, this is the flow rate that I'm using. The rate of dispersion is something you have to measure, and you do this in pulse tracer experiments. This is what you learn in your reactor design class, where you inject a delta function, or you inject a square wave, or you inject a step-up function. So you actually have to do that experiment. This was fun for us to do. You can inject hydrogen pulses on inert beds and calculate a dispersion coefficient for your bed so that you can calculate a Peclet number. Okay? You can do this, if you get another non-dimensional number. This is the rate of reaction to the rate of convection. This is the Dahm-Kohler number. The rate of reaction, I've already shown you how to measure. The rate of convection is simply the flow rate that I'm using. So I have a finite Dahm-Kohler number that I measure from kinetic studies. I have boundary conditions. We use closed backwards boundary conditions along the reaction vessel, except that for hydrogen, zirconium acts as a sink. And now I can start simulating reactor profiles as I go along. So if I simulate my reactor profiles, I can simulate the pressure of hydrogen and the reversibility axially along the length of the bed for different Peclet numbers. I get data that look like these, or I get results that look like these. If I look at an ideal PFR with a Peclet number of infinity, there's no effect. There's no benefit to adding the zirconium at the end of the bed. The only way I get a beneficial effect is that I have an axial profile that looks like this. This catalyst system has a finite Peclet number. Hydrogen has a very high dispersion coefficient. It moves. It conveys information along the length of the bed, which is not typical in a plug flow reactor. Okay? And you can see the virtue of adding zirconium. It allows me to remove hydrogen where I want to remove hydrogen, not where I must remove hydrogen, unlike in a membrane reactor. So I can calculate axial profiles along the length of the bed with the pressure of hydrogen, and that in turn allows me to calculate the methane conversion along the reactor bed. I measure, of course, only at the end of the bed. This is what I measure. This is what I simulate for the Peclet number that I have. So there's very good agreement between what I simulate and what I measure. I can do this for each of the reactor configurations that I've shown you. I showed you stage stratified beds. I showed you axially dispersed beds or intimately mixed beds. And this is the profile that I get. Again, those data are shown in the dots, and the profiles are shown by the simulations that I'm showing you. And again, you can see the virtue of adding an absorbent like zirconium. It allows me to remove hydrogen when I want to remove hydrogen. Okay? So we get nearly quantitative agreement between the model that we've developed and the effects that I see, but I can do further experiments to verify this. The non-dimensionalized equation that I had has terms that parameters that depend on the length of the bed, the Dahm-Kohler number and the Peclet number. They depend on the length of the bed. I should be able to vary the length of the bed and get a different answer. So this is the baseline case. I vary the length of the bed. I make the bed shorter. I get nearly quantitative agreement. I make the bed longer, And again, my model is able to describe the effects that I've shown you so far. I can do this in another fashion. I can take both the Dunn-Polar number and the Petlet number depend on the linear velocity that I use in my experiment. So I should be able to change my linear velocity and also see an effect on the catalysis if the axial dispersion coefficient is so high. Indeed, as I vary the linear velocity, I can again see that I can model these data nearly quantitatively. This is an experiment that we haven't been able to do, but we're very interested in doing so. Okay? So I'll try and summarize, at least I think I'm trying to get, so I'll try and summarize my talk. My goal was to show you this is an old reaction system. We are very interested in learning more about it. Our goals were to understand that what the reaction network was and to deconvolute the thermodynamic and kinetic influences that are involved in this catalysis. I hope I've shown you, at least on the basis of the data presented here, that it's a sequential reaction network. As the catalyst deactivates, it gives you information that the primary product is uniquely ethane. And it's that ethane that makes small quantities of acetylene that you see at low hydrogen pressures. And it's this acetylene that is involved in kinetically relevant steps. And it's these steps involving acetylene that are away from equilibrium. I can assess their kinetic influence by using the degree of rate control, where I do need to consider elementary steps that are involved in the catalysis. Steps involving acetylene that are kinetically relevant. Once I've figured out what the thermodynamic constraints are or the degree of rate control, I can try and identify a forward rate of reaction. This is an upper bound in catalyst performance. I have to be careful at what length scales I average things. But the true forward rate in this catalysis is constant, as it should be in a catalyst. And once I've addressed what the upper bound in catalyst performance is, then I can try and address the thermodynamic constraints that limit conversion in this catalysis. The thermodynamic restrictions for single pass conversion can be alleviated in a polyfunctional catalytic system. I can add absorbents. There are other ones that work as well that form metal hydrides at this high temperature. These hydrides are regenerable. And I can model this effect of adding absorbents by considering the finite axial dispersion that exists in a catalytic bed. And the polyfunctional strategy is determined, the effectiveness of that strategy is determined by hydrogen transport and dispersion. So with that, I'd like to thank the US Department of Energy for funding this research, and I will try and answer any questions you may have. Thank you for your attention.
We have time for a few questions. Yes.
Yeah, you revolved with talking about naphthalene as a byproduct of the reaction. The question is why and how do you deal with it in terms of selectivity and mechanism?
The data that I've been showing you in terms of the rates that I described in the second half of my talk when I was developing that axial bed model with hydrogen dispersion, that considers the rate to include both naphthalene and benzene. So I didn't try avoid talking about it. I just didn't bring that subtlety in as well. So the rates that we developed here, I'm just going back a couple of slides to show you. Yes, so we include the Dunn-Polar number for benzene and naphthalene. We're considering Dunn-Polar number is kinetics to linear velocity. We are considering the kinetics of naphthalene as well. We're considering the rates that I'm showing you are the cumulative rate of aromatics formed, including naphthalene.
Yes.
So how do you solve the carbon degradation on the zirconium reactor?
The zirconium does not deactivate the catalyst any faster. Does the catalyst itself deactivate? Yes. The zirconium itself, especially when we are a little strategic in placing it, I'll show you the data just to make back up my claim. When we're a little strategic in placing the zirconium, so these are the data that I'm interested in showing. This is the typical HZSM-5 catalyst. This is my catalyst bed with zirconium. The zirconium gets saturated, and you can see hydrogen breakthrough. But after the hydrogen is broken through, you can see that the rate of deactivation of this catalyst, this is the one with zirconium at the end, is exactly the same as the rate of deactivation of my typical moly catalyst. So the zirconium itself does not contribute to deactivation. Does the HZSM-5 catalyst deactivate? It does. We think where you remove hydrogen, you need a certain amount of hydrogen pressure at actually along the bed to make this catalyst stable. So there's certain advantages to removing hydrogen where you want to. This is a topic we're actively working in, so I won't talk much more about that. But we do think there's virtue in removing hydrogen at strategic points along the length of the bed to stabilize the catalyst further.
Over here.
So our impression, so the question is the moly carbide that I tried to show you in the TEM images, did that come from inside the catalyst, or is it something that we think came out from the dispersed bed, from the moly that was dispersed? My impression at these low moly loadings, we've done the TEM, and again I tried to show that, is that we think that it moves out, and that's why you regenerate the bronzed acid sites. So our moly to aluminum ratio is 0.25. We think you need low loadings of moly early on a high aluminum content material. Okay.
You didn't say anything about the regeneration and the service time until you have to regenerate the catalyst. Is that in hours? You said 50 hours it's running, and how would you manage that? Do you want to have an FCC unit to manage that in a larger scale, or can you comment on that?
I can comment. This is not, the reactor design part is not an area of expertise for me. If I have, so you can regenerate the catalyst in oxygen, 1% oxygen will regenerate your catalyst, the moly will redisperse, you have to carburize it again. So if I have a mixture of zirconium and HZSM-5, for example, zirconium has a density of the order of 6. The zeolite has a density of order 1 gram per cc. If you put this in a fluidized bed, yes, you could separate your absorbent and your catalyst, regenerate your catalyst in oxygen, regenerate your absorbent in hydrogen, recover your hydrogen from the zirconium, and put them both again together.
Yeah, but you cannot switch constantly a fixed bed reactor every few hours.
Yeah, the other option, it would have to be some sort of a moving bed reactor, is that I keep my moly and I keep moving my zirconium so that I get fresh absorbent so that my zirconium doesn't saturate. So I think there are other reactor configurations that would work as well. A little outside my area of expertise. That's the point I have to leave it at.
But we want to run it universally.
Yes.
Actually, we are out of time, so let's thank Aditya Bhan again